All right, so let's continue. So before we goes into the detail about matrix factorization, uh, let's say a little bit more about model-based approaches. So model-based approaches, just like what we have discussed just before, um, we somehow determine the estimation function of this Rxi, which contains a parameter. All the other things can be computed. I mean, it is deterministically. But for the parameter, we need to come up with a loss function or objective function and solve the optimization problem based on training data. And hopefully it works for the test data as well, or works in practice. So there are plenty of different techniques proposed in last few years, actually last decades, I guess. I think, yeah. So, for example, the matrix factorization techniques, or based on statistics, the idea is to do singular value decomposition or principal component analysis, association rule mining, which is a classic data mining problem. And it has been introduced in other CSE courses. And probabilistic models, for example, clustering models or Bayesian networks, which is not naive Bayes, it's another machine learning model, right? Or probabilistic latent semantic analysis, and various of other machine learning approaches. The cost of pre-processing for model-based approaches, for example, in this method, this BXI and BXJ, so basically BXI for any pair of X and I, are need to be pre-processed or pre-computed. Usually we don't discuss this part, although if in practice, if we want to implement such algorithms, then one of the few things that you need to consider is the update cost. So incremental updates means, for example, because the ratings or the users' actions are coming in like in a data stream, right? So we need to regularly update, for example, the BXI here, and this updates it is better to be incremental. Incremental in terms that we don't want to do it from the beginning, do the whole process over again. Instead, we want to, based on the current BXI and the new coming in ratings, to update the BXI to obtain the up-to-date BXIs. So if you decide to use such kind of model-based approaches, this issue is what you need to think about, and it is not trivial to solve. So before we have discussed the global efforts and some collaborative or nearest neighbor based algorithms, and the left part of this winner algorithm of Netflix prize is factorization. So matrix factorization, informally, it is based on the SVD theorem. So the SVD theorem states that a given matrix M can be decomposed into a product of three matrices as follows. So SVD here stands for singular value decomposition. So the idea is the given matrix M can be decomposed into a product of three matrices, which are U, and sigma and v. So here u and v are called left and right singular vectors. They are real orthogonal matrix, and this sigma is called the singular values. The values of the diagonal of sigma are called the singular values, and sigma here is a rectangular diagonal matrix with non-negative real numbers on the diagonal. So we can approximate the full matrix, which is M, by observing only the most important features, those with largest singular values. So in the example, we calculate u, v, and sigma with the help of some linear algebra software, for example, MATLAB or Python as well, but retain only the two most important features by taking only the first two columns of u and v transpose. I've reviewed the slides later and also the algorithm. So here should should be 3 rather than 2 in the example. But in fact, the author of that algorithm did not really use SVD. That's why we say informally here, because he claims that he's inspired by the SVD algorithm. The SVD theorem, but what he did is in fact factorizing a matrix into two other matrices and using the gradient descent to find optimal values of features and weights. So it is essentially not SVD, but the author choose to use the term anyway to describe the technique. That's why there are people still call the technique SVD, although it is not, strictly speaking, it is not SVD. So here, now let's look at the idea of matrix factorization. So what the author did essentially is to use two matrices, to use the product of two matrices to represent the matrix R. So R is the matrix of the rating matrix, and we know some cells of R, which are the yellow cells, we have the rating. For some of the cells, we do not have the rating, so there are white or blank cells. So this R would be a matrix of items times users. So we decompose R into two matrices, Q and P transpose. So for the matrix Q, the size is the size of items times the size of so-called factors. And for P transpose, it is the size of factors times the size of users. So that's why the product of Q and P transpose is would have the same size as R. Right. So items users, we all know what do they mean. But for the factors, the number of factors is a hyperparameter. So it is specified by the user or the designer of the algorithm. So here in the example we use 3, but in general, more factors or a larger factor number will lead to a better estimation of the ratings in this R. Although it also increases the cost of computation. So now let's assume that we can approximate the rating matrix R as a product of Q and P transpose. Right? For those missing entries in R, we ignore it for now. We ignore them for now. And basically, we will want the reconstruction error to be small on known ratings, and we don't care about values on the missing ones. So basically, the reconstruction error is that, for example, this cell, the value here should be the product of this vector and this vector, right? But if we do the computation, it would be 0.11 plus 0.32 plus this should be 0.42. So it would be 0.85. Right. Compare with the one here, the error would be 0.15. So this is part of the reconstruction error. So we would consider all the yellow cells here to do the computation and get the error. So we want the reconstruction error to be small on known ratings, and we don't care about those missing ones because we're going to do the prediction. So the next question would be how to estimate the missing rate of user X for item I. Assume this is the matrix R, and this is the Q and P transpose. So we know that Rxi equals to Qi times the transpose of Px, as the example that we have been seeing before. So it is essentially the sigma of the production of the corresponding cells. Now assume we want to estimate the values here. So this is the second line, second row, and the fifth column. So it's R25. So we know that the estimation would be the product of Q2 and transpose of P5. So it is this part, this vector, and this vector. And if we do the computation, we would have so 0.1 plus 0.18 plus it's 1 plus 0.18 plus 1.2, which is 2.38 or 2.4 here. Right. So the reason that we say matrix factorization is not SVD is because, as you can see, SVD is not defined when the entries are missing, but we can do it in matrix factorization. So we use specialized methods to find P and Q. By specialized method, here we actually the most commonly used optimizer is gradient descent. Gradient descent. So we know that this is how we estimate the ratings of Rxi, and so the loss function or the objective function is to minimize the reconstruction error or the total reconstruction error. Right? So we know that for a specific cell, the reconstruction error would be the estimated value or estimated rating, and the difference between estimated rating and the true rating. Right? So we do the square here, and we do the sum over all the known ratings. We want to minimize this summation. So this is our loss function. And we don't require the columns of PQ to be orthogonal or to be unit length, because such kind of constraints does not seem to be meaningful in this context. And also by ignore such kind of constraints, we kind of reduce the computation cost or the difficulty of the optimization of the problem. And we consider PQ maps users and movies to a latent space. For example, the Q here actually map the items or the movies to a latent space where these are the items. We still have this much items. In this example, 6 items. And for each item, we use a vector with some latent factors to describe the item. And for each and every user, we do the same thing. We use the factor latent factors to describe the users. You can also think these are some kind of latent features for items and users. That's why there are also some methods makes use of these latent vectors as the representations of the items and users, and to serve the other purposes. For example, as the input of a neural network or something. Although they won't be introduced in this course. So now let's look at the pros and cons of the collaborative filtering. So collaborative filtering works for any kind of item because there is no feature selection. Not unlike the content-based recommendation system, where we usually do it for document or text data. For this, by using collaborative filtering, because we don't have the feature selection step, it can be used for any kind of item. And even, for example, for matrix factorization, we even do not need to consider like what the features could be. We use a latent feature space. However, the collaborative filtering requires a cold start. Means it needs enough users in the system to find a match. It is obvious if you have not enough users, then you cannot properly learn the relationships between users or between items. So we do need a relatively large number of data or ratings. And the sparsity means that the user or the ratings matrix is sparse. Therefore, it is hard to find users that have rated the same items. So although I think we use the example here, where it is. Yeah, this one. Right. For example, if we want to know the ratings here, we want to know the ratings here for movie I by user 8. But for user 8, he only watches 2 movies. And if we found that, because for those movies that he have not watched yet, even we have a high similarity here, it does not help because we cannot use those movies to predict the rating of the movie 1 for by user X. We can only use these 2 movies But what if both of these two movies does not similar or does not similar enough to movie 1? In that case, we will not have a very accurate prediction of movie 1 by user 8. So this is what sparsity could harm the collaborative filtering algorithm. First rater, it cannot recommend an item that has not been previously rated. So it is kind of an extreme case of what we have just showed, especially for those new items or those esoteric items. Popularity bias. The collaborative filtering cannot recommend items to someone with unique taste. It tends to recommend popular items. So basically, the idea of collaborative filtering is is based on finding similar users or similar items. Depends on user CF or item CF. Which one are you using? But it always based on finding the similar users or items. So in that case, if someone has a unique taste, then it is hard to find similar users to him. Hence, it is hard to recommend items to him. Or for popular items, usually the popular items are. So we have more users who has bought them or watched them or rated them. Then it is we would be able to have a better estimation for these items. But for the rare items, we don't have enough data, so the estimation would be not that reliable or accurate. So that's pretty much for collaborative filtering, and also the winner prize of the Netflix competition. And the last part we're going to introduce is the knowledge-based recommendation. So the knowledge-based recommendation, the main difference between knowledge-based recommendation from those we have been discussed before is that it uses knowledge models. It uses knowledge models to enhance the recommendation process. So the main idea of knowledge-based recommendation is to tell the user what what item fits his needs what item fits based on the user's needs. So why do we need a knowledge-based recommendation? So we need it when we're dealing with products with a low number of available ratings, or say those unpopular items, right? So this so knowledge-based recommendation is used to help handle those cases that collaborative filtering cannot do very well, right? And also it can be used when the time span plays an important role. For example, we want to know the 5-year-old ratings for the computers, or we want to do the prediction. However, the user's lifestyle or the family situation changes. In that case, collaborative filtering may not be able to aware such kind of changes or such kind of situations. However, if we can embed the knowledge into the recommender system, then we might be able to handle this such cases. Also, we use it when the customers want to define their requirements explicitly. Right? For example, the color of the car should be black. In that case, we shouldn't recommend cars with other colors to the user. So there are several ways to do the knowledge-based recommendation. One is constraint-based. So it's based on explicitly defined set of recommendation rules, and the recommender system is supposed to fulfill all the recommendation rules. For example, when I want to buy a car, in car sales, for example, then I may have specific requirements. For example, I want a black car. I want the make to be Toyota or Honda, right? And so the recommender system must fulfill all these rules or requirements before it produces recommendations. Right? Another way of doing knowledge-based recommendation is case-based. So it is based on different types of similarity measures and retrieves items that are similar to specific requirements. So the idea is, for example, my father and I did both search for a car in car sales because we search from different devices, and we don't know the other one has done the search as well. But our requirements would be quite similar. So let's say my father searched first, and when I do the searching, the recommender system actually recognized that my requirements are quite similar to my father's. Then it can use the previous information and also the feedback of the previous users to build the recommendations for me. So it's more like a case-by-case situation. Right? So the idea is to find similar cases and then do the recommendation based on these cases. So by cases, we usually consider the similarity to a specific requirements. So both approaches are similar in their conversational recommendation process, where the users specify the requirements, the system try to identify solutions. If no solution can be found, users change their requirements. So it really looks like what the users. From the user's perspective, it's really similar to my experience on car sales. Right? I give the input of a set of requirements, and some of them may be contradict with each other. And if there is nothing output by the system, then I will need to change the requirements, and then hopefully we will see some outputs or some recommendations. And also, as in the car sales website, I guess it does use a hybrid methods of knowledge-based recommendation system and other recommendation techniques, right? Because when you have given the system a set of requirements, it gives you the results, and these results have an order, right? Have an order. And unless you specify the order, otherwise the order it gives you should based on the output of the backend recommendation system. Right? So for the hybrid methods, we can there are several ways to hybrid different recommendation systems or recommendation algorithms together. One way is to implement 2 or more different recommenders and combine the predictions. When we combine the predictions, perhaps we can use a linear model for example, if say we have 3 recommenders, and the prediction for the same item by the same user, let's say it is 2.5, 3, and 3.2. In that case, if we use a linear model, we actually use different coefficients like alpha, beta, and gamma. And then we can get our final prediction of the item by the user, right? Although this alpha, beta, gamma, we can learn it, or we can specify them as hyperparameters. Right? And another way is to add content-based methods to collaborative filtering. Because we know that collaborative filtering works well unless we don't have enough data because of the sparsity of the rating matrix, especially when we are dealing with a new item or new user. Right? But content-based method does not have this kind of struggles. So we can use collaborative filtering to handle most cases, but for new item, we can use item profiles and use content-based methods to do the prediction. For new users, we can do the prediction based on the demographics to deal with them. So that's pretty much all for recommendation systems, and also for this 9313 course. Right, so it seems that we still have some time, so I will address some questions on the PIADA, and then I will give some instruction about the final exam. All right, so let's first to deal with the questions. So I posted a note on PIADA in order to collect questions from you, and so far I've only got two questions, both related to the contents in lecture 8. Right. So the first question would be, so given the process of updating buckets, how do we assign the bucket at the beginning? Right. For example, when the arrived data size is smaller than the window size. So the answer would be easy. Let's say let's assume this one is the beginning of the stream. Okay. So we start from this one, and we start to bucket or bucketize the stream, starting from a bucket with size 1. So this would be a bucket, this one. And for 0, we just ignore it. And here we see another bucket. Here we see another one. So we create another bucket with size 1. So far, we've got 4 bits in the data stream, right? And we then see the third one. We build another bucket with size 1. So far, we've got 3 buckets with size 1. So according to the updating policy, we need to, when we have 3 buckets of size 1, we need to combine the oldest 2 and build a bucket of size 2. So we will combine these 2, right? And so we've got a bucket of size 2 and a bucket of size 1. Then we will do it over and over again. So what if the window size is larger than the size of the stream that we've seen so far? So in that case, say the window size is like this much, and we're still at this position, for example, then we can actually get an accurate answer to the question, because essentially we've got everything in the window, so we can get the accurate answer. So that is the reply to this question. And the second one, could you please go over lecture 8 slides 16 and 17 on sampling a fixed proportion again? Okay, how to calculate the fractions of pairs of duplicates and duplicates occurring just once on slide 16, and how to how sampling users instead of queries solves the problem. All right, so let me see here. The naive approach, where we sample based on the queries, right? So we just sample 1/10 of the total queries. So the problem here is that let me see. Now we consider we have x plus 2d queries. So this is the scenario we are considering, and for this x plus 2d queries, we have x queries which only occurs once, and d queries occurs twice. So we have x plus d different queries, and how much of them are duplicates or occurs more than once, d of them. Right. So this would be the correct answer that we expected to get. Now with the solution of keep 10% of the queries, see what we have. So we're expected to sample x over 10 of the singleton queries. So those queries occurs only once, and 2d over 10 of the duplicate queries. Right. And we need to answer this question based on our sample. Let's say we have query 1, 2 to 10. These queries occurs only once, so these are the x. And we have 11, 12 to 20. These are the d queries. So essentially we have 2 of them. So these are the 2d queries, right? So we are expected to sample, because we keep 10% of the queries, so we're expected to sample 3 queries, right? And one of them expected to be from x. So either one of them is from 1 to 10, and 2 of them are from 11 to 20. Since we will answer the question of what's the fraction of queries are duplicates purely based on the samples we have, right? So we need to compute like the probability of we observed a duplicate in our sample. So as we will sample 2 queries from this part. So we firstly sample 1 over 10 or 10% of this d queries, and then within this 10%, only 10% of them will be selected twice. So that's another 10% times this 10% of d. So it would be 1% times d. So in this example, if we do the similar computation, the total number of possibilities, like 11, 11 is 1, 11, 12 it's 2, and so on and so forth. So it should be 10 times 10. So in total, 100 different situations. And how many of them are a duplicate? Right? So only 10 of them. Right? Either we got 211 or 212 or so on and so forth. So it's 1 over 10. Right? If we do the and in this case d equals to 10. So if we plug in 10 here instead of d, we would get 1 over 10. Right? So it's 10 over 100, which is 1 over 10. These two are the same. And for deduplicates queries which appear only exactly once, the idea is similar. I mean, for those 10% times D queries which has been sampled once, they would have 90% of the probability that will not be sampled anymore. So they will be sampled and only once, right? And for those 90% times D queries which has not been sampled yet, in contradiction to this 10%, they will have another 10% chance to be sampled. So this and if they were sampled, these queries will appear only once as well. So we add them together, we would have this 18 times D over 100. Then we can have this answer. So that is for this slide. And why sample based on users will solve the problem? Because we're considering what the fraction of queries by an user are duplicates. That's why if we pick 10% of the users and take all their searches in the sample, we can answer this question, because the question is asked about the fraction of queries by an user. But if we sample on queries instead of users, even in this case, we only consider one user, this kind of sampling will not work. Hope this time it would be more clear. And these are the questions I've got so far, so hopefully I've addressed them properly. And a little bit more words about the final exam, although we will, some more detailed instructions of the final exam is on the way. The exam is scheduled on 19th of August. It will start from 12 p.m., which is the noon. This is Sydney time. All right, this is Sydney time. And the exam will last for 24 hours, although the workload of the exam is not expected to be 24 hours. I do expect you can finish the exam just like your normal exams when we have the face-to-face final exams. So 2 to 3 hours should be enough. But if you would like to use more time, it's okay. Just make sure you have submitted your answer sheet using GIF by 12 p.m. Of 20th of August. Right. And the questions of the final exam will be published on Web CMS 3. So this is probably the first time we use Web CMS 3 system in this course. But this is because the school does not allow us to use Google Drive to publish the exam paper. So it will be published on the school's teaching system. In this case, I mean, from now on, the notices will be published on both Web CMS 3 and the course website. I think also I will put a copy on Piada as well. So please check the notices regularly in order to not missing anything. All right. And if you need a special consideration, apply it now. All right. Here is the link of how to apply for a special consideration. Don't email me, because I'm not the one who can make the decision. You need to email the university, and because it usually takes several working days to process your special consideration. So if you want to apply it now. All right. Don't wait. and don't, for example, tell me that you need an extension or you need a supplementary exam or whatever. Say on the same day of the exam or on one day before the exam, I can do nothing. If you need, just ask the university, and do it soon. So that's all for today's lecture. Next week, we will have a revision lecture to help you go through all the contents in this course, and we will offer more details about the final exam. Or if you are concerned about your marks of the assignment and probably the project, don't expect the marks will be released, say, before next week. But we will try our best to release the marks before the final exam. And if you have any, after we've released the mark, if you have any questions, I do suggest you wait after the final exam. It is still it will be fine, and we can modify the scores if it is necessary. So just focus on the coming deadlines and the final exams. Don't waste your time on arguing about your scores or marks on these assignments and projects. So that's all for today, and see you next Monday.